Welcome to Remote Learning for STAT111. I just wanted to review one more time the tentative plan. So there'll be Tuesday and Thursday live class meetings. Had the first ones today. They went reasonably all right, I think. If you have any feedback, please let me know. Hope you can join us if you didn't this time. There will be online office hours available Monday from 1 to 2 and Wednesday from 7 to 8, and then by appointment at other times. I have a lot more flexibility in my schedule now, so please let me know if those times don't work for you and you'd like to talk, or if you want to talk about something that is of a more personal nature and you don't want to do it in an office hour that other people can listen to. Just as a note, these are office hours that are dedicated for STAT111 students only. So we won't have students from my other courses there at the same time. So it'll give you more sort of focused attention. The reading questions and homework schedule I posted on Blackboard a few days ago. It has been updated from the original one at the start of the semester. The due dates have also been updated in Wiley Plus. The remaining quizzes, I think there were 2 left, will be on Blackboard. They will have 30-minute time limits, which should be lots and lots of time for most of you. There'll be no proctor and there'll be open notes, and you can use a calculator on them. They're actually not just the final exam, but another in-class, what would have been an in-class exam. Both of those will also be online with no proctoring and no notes. I'm going to set the time limit to be ample for both of them on the final. There'll be a 3-hour time limit, even though the exam is intended to take at most 90 minutes. For the other exam in April, I'll probably have a 2-hour time limit for something that was intended to take an hour. So should be plenty of time to do both of those. Just mention that I know people have a variety of different situations going on depending on what's going on with your family and where you're living and all kinds of different things. If you have anything going on that you think I can help with by being flexible or doing something specific to help you, just let me know. I'll do what I can. So we have been talking in this unit about statistical inference, and in particular, so far we have looked at confidence intervals, which are sort of in the branch of inference that we think of as estimation. And confidence intervals, remember, we're telling us, okay, based on the sample data, what's a range of plausible values for the population parameter? What we're going to focus on in Chapter 4 is on hypothesis testing. Hypothesis test tells us how strongly the sample data support a claim about the population parameter. And so we'll start Chapter 4 with Section 4.1, which is called Introducing Hypothesis Testing. First of all, when we talk about a statistical hypothesis test is something that uses data from a sample to assess a claim about a population. So for example, I might do this informally in my own life. I have a friend named Eric who is a bowler, and he claims that his average is over 180. And, you know, I'm not much of a bowler myself. In fact, I'm the gutter ball queen. But in any case, 180 I know is really high, and so I'm a little doubtful that Eric's average is above 180. So we go and we bowl 2 games, and Eric's scores in the 2 games are 170 and 191. And when I average those 2 numbers out, calculate the mean, the average is 180.5. So that is over 180, but I'm not convinced that he's average, really, his ability is over 180. I mean, maybe he's just a 170 bowler who had a lucky game, right? It's only 2 games. It's barely an average over 180. I'm not sure that he's really better than that. So we bowl some more. And after 20 games, Eric's average is 188 points per game. Now I'm convinced. I'm pretty sure that his bowling average really is above 180. So here I'm using data, right? What happened in the games that we actually observed to try to evaluate how strong the evidence is to support Eric's claim that his average is over 180. Now, to more formally begin hypothesis testing, we are going to need to learn how to formulate the hypotheses to be tested, and we call those the null and the alternative hypothesis. The null hypothesis, which we give the notation H sub 0, H sub 0 there, often represents the idea that there's no change from status quo and that the results that we saw were due to sort of random chance. And the null hypothesis is always written in terms of the parameter because it's about what it might be true in the population. So it's always that a population parameter is equal to some null value. The alternative hypothesis, which we give the notation H with an A subscript, is the claim that we seek evidence to support, and it's always a statement that the parameter differs in some way from the null value. So in our bowling example, the claim that we were trying to see if there was evidence to support was Eric's claim that his bowling average is above 180. So that would be, in terms of notation, that the population mean is greater than 180. So here, the parameter is the mean, differs from, by being greater than, the null value of 180. And so our null hypothesis is that Eric's bowling average is 180. Mu is equal to 180. So again, we always have an equality sign. In the null hypothesis. Now, when we're thinking about evaluating how strong the evidence is, we do it by considering how consistent the observed result, and by the observed result we mean sort of what happened in the sample, is with what we'd expect to see if the null hypothesis is true. So if the sample is reasonably consistent with the null hypothesis, we'll say, well, this seems like something that might have happened just due to chance, and we won't reject the null hypothesis. We'll conclude that it's plausible that the null hypothesis might be true. So, for example, when Eric scored 170 and 191 on the two games, it seemed plausible that he's a 180 bowler rather than a better than 180 bowler. On the other hand, if the sample is very inconsistent with the null hypothesis, then we'd say that the null hypothesis is not plausible and we reject it. In this case, Eric's average after 20 games was 188, which seems pretty unlikely to be that high if he really isn't better than a 180 bowler. So it gives us strong evidence to believe that his average really is above 180. Now, this sort of reasoning might seem a little bit counterintuitive at first, and don't worry if it does. We're going to be working with it for a long time. And it, kind of feels that way to most people. And that's because in statistics, we show things in a strange way. We use a kind of double negative kind of thinking. If we want to show that there's a difference between two things, right, just thinking about what that would look like in terms of our hypotheses, without being more specific, we'd have our null and our alternative hypotheses. We're trying to show there's a difference. So the null would be, the alternative, what we're trying to support is that there is a difference. And the null would be that there's no difference. So in order to show that there's a difference between two things, we try to show that the data are inconsistent with the null hypothesis so that we can reject it. And then we say, well, if there's no difference, then there must be a difference. All right, it's a very strange way of doing things, I understand, but we'll talk more about why we do it that way as we get into the next section. So quick example, we have college students. Are they sleeping too little? It's recommended that young adults sleep 7 to 8 hours per night, and a researcher asks a random sample of college students how many hours of sleep they got in the previous night. She wants to determine how strong the evidence is that the average hours of sleep per night for college students is less than 7. Now, because the hypotheses are always about the parameter, we always need to start, before we can write our hypotheses, we need to identify the parameter of interest. Now here she's recording the number of hours of sleep. So that's one quantitative variable. So the parameter of interest is going to be the population mean. Mean hours slept among all college students. Something along those lines. Now, to write my hypotheses, it's customary to write the null hypothesis first and then the alternative hypothesis. But the research question itself usually leads us towards the alternative hypothesis. So I write them this way, but I'm going to fill in the alternative first. So she wants to determine how strong the evidence is that the average hours of sleep per night for college students is less than 7 hours. That's going to be my alternative. Okay, so writing that in terms of my parameter, that would be that mu is less than 7. And remember, my null is also going to be mu is equal to that same value that I was less than in my alternative. So mu is equal to 7 hours. Now, as I'm looking to see which sample means gives the strongest evidence against the null and in support of the alternative, here's a sample mean of 7. That's equal to the null, so that's not giving any evidence against the null. A sample mean of 10 is not equal to the null, but it's not in the direction of the alternative, so it doesn't support the alternative hypothesis. The value that would give me the strongest evidence that the mean number of hours slept among college students is less than 7 hours is going to be the sample mean of size 5. And if the test shows strong evidence against the null hypothesis and in favor of the alternative, what that will mean is that there will be strong evidence that on average college students sleep less than 7 hours per night. This is what we call a left-tailed alternative hypothesis. Remember that our null hypothesis was that the mean is equal to 7 hours, and our alternative was that the mean is less than 7 hours. When we have a less than type of statement in the alternative hypothesis, that's called a left-tailed alternative, and this will become important in section 4.2, but for now we'll just sort of leave it at that. Being able to identify that it is in fact left-tailed. At this point, if you didn't attend the live lecture online, I recommend that you stop the video, go to the worksheet, and try doing these examples on your own. At least try to do 1 or 2 of them and watch the solutions to those, maybe before you go through and finish the rest. But make sure you've got the hang of it after a couple, but definitely make sure that you're trying to work through these on your own and not just sort of watching me, because it's a lot easier to watch than it is to figure things out for yourself. And it's good to start getting some practice doing that. So for the first example, the first thing I needed to do was identify the parameter. And I did this by first of all figuring out what variables were recorded. And those were the categorical variable, whether the person was a 5th grader or an adult, and the quantitative variable, which would have been the number of multiplication facts that each person could remember. Once I identified those, I knew that the parameter of interest must be a difference in means. And so it would be the difference in the mean number of multiplication facts between 5th graders and adults. And remember, I always have population notation when I'm talking about the parameter, because a parameter, P for parameter, P for population, parameter is summarizing a characteristic of the population. Now that I'm ready to write my hypotheses, I know my hypotheses are going to be determined by the research question. So, can 5th graders answer more multiplication facts per minute than adults? More multiplication facts per minute than adults. The research question is always giving us our alternative hypothesis. So, the alternative is 5th graders more than adults. So what that would mean would be that if I take the mean for the 5th graders and subtract the mean from the adults, if the 5th graders is higher, this is going to have to be greater than 0. Or I could equivalently write this as the mean for 5th graders is greater than the mean for adults. Now that I want to go back and write my null hypothesis, my null hypothesis is going to be that the parameter is equal to the null value, which remember, null value for the parameter is here. It's greater than, in the situation in the alternative, the null value. So mu1 minus mu2 is equal to 0. No difference in how many math facts they can remember is the null. And I could write that again alternatively as mu1 equals mu2. Either one is correct. Now notice that in this situation, we had a more than kind of statement in our alternative hypothesis. This is what we call a right-tailed alternative. When the alternative hypothesis is that the parameter is more than the null value, that is a right-tailed alternative. The second example we saw is looking to see if there's an association between whether a person takes aspirin daily and whether a person will have a heart attack. These are looking for an association between 2 categorical variables. So the parameter of interest is a difference in proportions. It's the difference in the proportion who have a heart attack between those who take aspirin and those who don't. And I called the aspirin group the group 1 and the no aspirin the group 2. So when I'm looking to write my hypotheses, remember my research question is always going to give me the alternative hypothesis. So is there an association between the variables? The association is going to be my alternative hypothesis. No association is going to be the null. If there were no association, then there should be no difference in the chance of a person having a heart attack between those taking aspirin and those not. So the difference in proportions would be 0, or equivalently, the proportions would equal each other. If there is an association, it doesn't indicate whether it's looking for a positive association or a negative association. So all I know is that the proportions would not be the same in both groups. that the difference would not be 0, or I could write this as P1 is not equal to P2. Now, when the alternative hypothesis doesn't indicate a direction for an association, that is what's called a two-tailed alternative. So the alternative hypothesis is that the parameter is not equal to the null value in a two-tailed alternative. Example 3 is usually a tricky one for people. This one's looking at whether cats have a preference between eating from an orange bowl or a gray bowl. 100 cats were given their choice between eating from a gray bowl or an orange bowl, and each cat's choice was recorded. So this is only one categorical variable. I'm going to be recording gray or orange. And so since it's one categorical variable, my parameter is not a difference in proportions. A difference in proportions is useful for comparing two separate groups, but I only have one group of cats here, so my parameter is going to be P, a single proportion. It'll be something like the proportion of cats who prefer orange bowls. Now, why orange and not gray? It actually isn't going to matter at all which category I choose, because if I know the proportion of cats who prefer orange bowls over gray, the other ones would have to be ones that would choose gray over orange. So it's not going to make any difference which one I choose. But the thing that is important is that I recognize that with only one categorical variable, I only want to make inferences about one proportion. Okay, so how can I do that in this situation? Do cats have a preference? Okay, so the cats have a preference. Is going to be my alternative. And the cats having no preference is going to be my null. Now, if the cats have no preference whatsoever between the two, then they're just choosing randomly from two possibilities, and I'd expect that the proportion of cats who would end up choosing the orange bowl would be 0.5. Compared to the alternative, if cats have a preference, doesn't indicate which one they prefer, just that they have some preference, so that would be two-tailed. Either the cat P would be greater than 0.5, which would indicate that cats prefer the orange bowls, or P would be less than 0.5, which would indicate that cats prefer the gray bowl. So this is a two-tailed type of test. Example 4. Do people who practice yoga tend to take fewer sick days per year than those who don't practice yoga? Okay, so to answer this question, I'd have to record two things. I'd have to, for each person, I'd have to record whether they practice yoga or not, which would be a categorical variable. And I would need to record the number of sick days that they take per year, which would be quantitative. And with one categorical and one quantitative variable, the parameter of interest is going to be a difference in means, mu1 minus mu2. And that's the difference in the mean number of sick days between those practicing yoga, which I'm going to call group 1, and those not practicing yoga, which I'm going to call group 2. So now writing my hypotheses, do people who practice yoga tend to take fewer sick days? Okay, so if people taking yoga take fewer sick days, that would mean that mu1 is less than mu2. So when I subtract mu2 from mu1, I get something that's less than 0. Or, writing that another way, mu1 is less than mu2. And my null hypothesis is going to be that the means are equal, or that the difference in means is equal to 0. And then our last example, we're looking to see, is there a linear association between the number of people living in a household and the number of pets living in a household? Here we have two quantitative variables. We're interested in a linear association, and the strength and direction of a linear association, remember, are measured with the correlation. So our parameter is going to be the population correlation rho. Writing our hypotheses. Is there a linear association? So an association existing is going to be our alternative. No association is going to be our null. If there's no linear association, then rho would equal 0. And I should specify this as no linear association. And this would be indicating a linear association. And if there is a linear association, now I need to look, does it specify the direction? No, it doesn't necessarily say what type of household will have more pets. So without specifying direction, the correlation would be not equal to 0. Well, I hope that working through this video is helpful to you as you're getting started in Chapter 4. There is homework on Section 4.1 that is due next week. And in Tuesday's class, we'll get started on 4.2, where we'll learn how to start measuring how strong the evidence is against the null hypothesis and in support of the alternative. I look forward to talking to you then, if not sooner. Have a good day.